are watching Cam Science.
In this video, let's discuss question paper 52 of 9701 chemistry examination series October-November 2024, that is winter 2024. But before we go ahead, let me also tell you that we have also an chemistry app, an Android app on the given link shown here, and then the link is also given in the description of the video, where for each and every topic of the latest syllabus of IGCSE, we have an updated notes, videos, lots of videos for each and every topic. Then we have topical MCQs where you will get the answers also and your score also at the end of the MCQ tests. For each and every topic we have enough tests separate for core and extended. Similarly, we have separate core and extended subjective test also. Along with that, we also have revision tests, that is you can take a revision test for your selected topics only. So that is how you can revise also. Plus we have ample of past papers on the same app. So altogether all the resources on the one app itself, and the link is given in the description. So you can go ahead and download it, and let's go ahead to solve the question paper 52. So here is question 1 of the question paper 52 of the examination series 2024 October-November series. The question 1 is, solution X is a dilute hydrochloric acid of unknown concentration. A student uses titration with aqueous sodium carbonate to determine the concentration of solution X. Now X is hydrochloric acid, and we are supposed to determine the concentration of hydrochloric acid with the help of titration with sodium carbonate. Okay. The student plans to prepare 250 centimeter cube of 0.50 moles per dm cube of aqueous sodium carbonate, that is Na2CO3 in aqueous form. The question 1a is, calculate the mass of sodium carbonate needed to make 250 centimeter cube of 0.5 moles per dm cube sodium carbonate using a 2 decimal place balance. Now for that, first we need to calculate the relative molecular mass of sodium carbonate. To calculate that, you can refer the periodic table which is given at the end of this question paper. I have already done that, and so let's substitute all the values. That is, sodium is 2, so we can multiply 2 with the relative atomic mass of sodium, which is 23, plus the atomic mass of carbon, that is 12, plus the atomic mass of oxygen, which is 16, multiplied by 3 because here we have O3. Now this is equal to 106 gram. Now the simplest way from which we can calculate the mass is that if we want to prepare 1 mole per dm cube solution in 1000 centimeter cube, then we use this MR, that is 106. So if we want to prepare a concentration of here 0.50 multiply by the volume, that is 250 centimeter cube, then how much of the mass will be using? So you just need to cross multiply all this, and you can find out the mass is equal to 106 into 0.5 into 250 divide by 1000. That's what we get, and if we calculate all this, we get the answer as 13.25 gram. Now they have already written 2 decimal place balance we are using, so accordingly we have to give the answer. So to 2 decimal place we have got the mass as 13.250 gram. Let's see what is the next part. It says, describe how the student should make 250 centimeter cube of 0.5 moles per dm cube sodium carbonate, starting from the mass of sodium carbonate calculated in one supplied in 50 centimeter cube beaker. Give the name and size of any key apparatus to be used. Write your answer using a series of numbered steps. Now you can see that the mass is already supplied in 50 centimeter cube of beaker. So what is the first step is that add small volume of distilled water to the solid in the beaker. So to the solid in the beaker we are adding a distilled water. Remember, we need to specify distilled water, and stir and dissolve it, and stir and dissolve it. So first step is that whatever solid we are supplied, we are dissolving it into small amount of water. Then transfer the solution, transfer the prepared solution, whatever we have prepared by dissolving the solution, that solution, transfer the solution into 250 centimeter cube of volumetric flask. Now as we are specifying that we are preparing 250 centimeter cube of solution, so we have to use 250 centimeter cube of volumetric flask for this preparation. Now along with this transferring of solution, we also need to transfer some of the washings of the same beaker with the distilled water. So what we are going to do is transfer the solution to the 250 centimeter cube of volumetric flask, again add little of the water every time to the beaker, and again transfer that to the volumetric flask. That's called the washings. So 2 to 3 such washings we need to transfer. So we'll write that also, that along with 2-3 washings. That's what we can write it in short, along with 2-3 washings. And what are we going to do is add distilled water to the volumetric flask, to the same volumetric flask of 250 centimeter cube, 250. So add distilled water to the volumetric flask up to the mark. There will be a mark which shows the volume of 250 centimeter cube on the volumetric flask. So up to that mark we are going to add distilled water and then shake well. That is the how we're going to prepare the solution. So this is a 3-mark question, and you can see we have written 3 important points to describe the preparation of this solution, right? So this is how you have to describe it stepwise. Now sub question B is the whole procedure, where it says that students incorrectly makes up to 250 centimeter cube of sodium carbonate and the concentration is not 0.5 mole per dm cube. The student calls this solution Y. So again, understand, the solution Y is also sodium carbonate, but it is not prepared properly, and so the solution is not exactly 0.5 moles per dm cube. Okay. The student uses the following method to determine both the concentration of solution X and the concentration of solution Y. Okay. Transfer 25 centimeter cube of solution Y in conical flask using volumetric pipette. Add a few drops of methyl orange and titrate the sample in the conical flask with solution X. Transfer a fresh 25 centimeter cube portion of solution Y into second conical flask, but do not add methyl orange. Use the burette to add the volume of solution X used in step 2 to the second conical flask. Okay, so what are you doing? You are again taking up the same volume of solution Y in the another conical flask. Remember, we are using second conical flask, but we are not adding methyl orange. From the burette we are using to add the volume of solution X, which we had noted down in step 2. Step 2 we had titrated and we had noted down some volume of solution X required for the color change. Same volume we are adding, but without the indicator now, and then that is how we are repeating the step 2 here. Measure and record the mass of a dry evaporating dish. So we are now taking an evaporating dish, we are measuring its weight. Transfer the content of the second conical flask into evaporating basin. Use a water bath to heat the solution in an evaporating basin until all the water has evaporated, only solid remains. Measure and record the mass of the evaporating basin and solid residue. So that's how we are going to find out the volume, or you can say concentration of solution Y. Okay, so in step 1, 25 centimeter cube of solution Y is transferred using volumetric pipette. State what the volumetric pipette should be rinsed with before carrying out step 1. So if we are transferring solution Y with the help of pipette, you should also use solution Y to rinse the pipette same Y, because there should not be any other solution or distilled water which we have used to wash the volumetric pipette remaining in the pipette. So we will wash the pipette with solution Y, and then we will transfer 25 centimeter cube with the help of pipette to the conical flask. Okay, describe how the student detects the endpoint of the titration in step 2. Now step 2, we are adding methyl orange and then titrating it with the help of solution X. So how to determine the endpoint? So obviously the indicator methyl orange will show the color change. So methyl orange will change color or will show a color change. That's what you can write in both ways. Okay, third part is explain why the evaporating basin is not heated directly in a Bunsen burner in step 7. The reason is that when the solid starts forming after when the water has almost evaporated, then we can see that direct flame, that is direct heat, might spit the solid which has formed on the sides of the evaporating basin, because we'll observe that when the water starts evaporating, the sides of the evaporating basin starts getting the solid on it, and when we heat it directly with the flame, this solid might start spitting it. So to avoid that, we heat it up in an water bath so that direct flame doesn't affect the solid. So we can directly write to avoid the spitting of the solid, in the evaporating dish due to direct flame of the heat. Okay, yes, see. Okay, suggest what the student should do to ensure all the water has evaporated from the residue before completing step 8. So what we can do is that after the water has evaporated, we can weigh it and again heat it gently and then again reweigh it. Now if we do this heating and weighing again and again, that's called heating up to the constant mass. So we can write it here that to suggest what shouldn't to do, we should reheat and cool till constant mass, that is keep on heating and cooling till it gives a constant mass after heating of the evaporating basin. Let's see what's ahead here with us. Okay, the students' burette readings taken in step 2 are shown in figure 1.1. So here we have two burette with the initial and final readings to show us the burette of both the readings. Okay, so use figure 1.1 to complete table 1.1, the burette reading final. Now final is burette reading shown here. Now we need to understand that whenever we are reading the burette, it has to be the lower meniscus which should be read. Okay, so we can see that there is just 1 mark less than 15. Not even 1 mark. You can say that this is the last mark of below above 15, and this is the second last mark, and this is in between the 2 marks. So you can say that here it is 14.8 and here it is 14.9. So in between our final reading should be 14.85, that is to 2 decimal place we are writing. Okay, for the initial reading, yes, we can say here again it's between 1 and 2, so this is 1.1, 1.2, 1.3 and 1.4. Again the lower meniscus is between 1.3 and 1.4, so our initial reading also should be 1.35. So now if we calculate the volume of solution added in centimeter cube, that is we have to subtract this, then we can say that it is The subtraction answer is 13.50, that is 13.50 centimeter cube. That's the difference between the initial and final readings of the burette. Okay. Calculate the percentage error in volume of solution X calculated in 1 and show your working. So what's the volume which we have calculated is 13.15. So 13.50 is the volume which we have used in our first answer. And what is the maximum error of the burette reading? Now in the burette reading marks, we have seen that we can't exactly read 0.05 centimeter cube because it is between the two marks. So that's the maximum error will come across. But as we have used the burette twice to get this reading, so our error has been repeated twice. So we have to multiply the maximum error with 2 and then divide it by the reading which we are using for the further calculation, and then multiply it by 100 to calculate the percentage error. And this gives us the answer of 0.741 percentage. So that's the percentage error which we have calculated for our given reading of 13.50. Let's go ahead, see the next question, next part. A second student repeats the experiment in B using solution X and 25 centimeter cube of solution Y. The results are shown in the table 1.2. The volume of the solution X added in titration is 13.35. Okay. Mass of the dry evaporating basin is 44.52 gram. And mass of the evaporating basin plus solid residue is 45.69. Okay. The reaction takes place in the titration is also given here. Using the results in table 1.2, that is the table given here, calculate the following. So let's go ahead, calculate the amount in moles of sodium chloride. Now what is the sodium chloride? Sodium chloride is a residue formed here. So what is the volume of the residue formed? So first calculate the mass of the residue by subtracting these two values. That is, subtract the total mass by subtract the evaporating basin mass from the total mass to get the mass of only solid residue, that is sodium chloride. So for that, 45.69 minus 44.52, and that is equal to 1.17. Fine. Now if we calculate the MR, that is relative molecular mass of NaCl, then we have 23 plus 35.5, and that is equal to, you can say that on addition we get 58.5 gram. Now to calculate the moles, we have N is equal to M upon MR, that is mass upon molecular mass, that is 1.17 divided by 58.5, and that is equal to 0.0200. Now I'm using three significant figures, that's why I'm writing 0.0200 moles. Remember, always try to use three significant figure answer everywhere. So the next question is, calculate the concentration of solution X and the concentration of solution Y here. Now if we are calculating concentration, we need to have moles and then the volume, because the formula of concentration is moles divided by volume. Now we have got the moles of sodium chloride. From that we can calculate the moles of solution X, that is HCl. So if we have equation here, you can see that there is the ratio of 2:2 moles for both HCl and sodium chloride. So the moles of sodium chloride is equal to the moles of HCl. So here for the concentration of HCl, we have moles 0.0200 itself divided by the volume of HCl which we have used here. Now what's the volume of HCl? Volume of HCl is the titration volume which we have used here, and that is 13.50 titer volume, because in burette we had filled up HCl. So volume is a 13.50. But 13.50 has to be divided by 1000 to change it into a dm cube. and here the answer is equal to 1.48. so that is the concentration in moles per dm cube for the solution X. So we can write here 1.48 moles per dm cube. Now we need to know the concentration of solution Y, and for concentration of solution Y, that is sodium carbonate, if we again check the equation, yes, compared to sodium chloride, sodium carbonate used is half the moles, because here the ratio is 2 and the ratio of sodium carbonate is 1. So 1:2 ratio. So the moles should be half of the moles used here. So the moles will be 0.0100 and divide by the volume of sodium carbonate solution, that is solution Y used. Now that is what we have taken in the pipette. So the pipette volume is 25 centimeter cube. So again divide by the volume, that is 25 into 10 power minus 3, because we again need to divide it by 1000 to change it into dm cube. And so our answer here is 0.400. Again I'm writing three significant figures, so I'm writing 0.400, right? So that's the concentration of solution Y, that is sodium carbonate, 0.400, and the concentration of solution X, that is HCl, is 1.48 moles per dm cube. Here you might get 1 point, say similar to 5, depending on the dp's decimal place you're using in the calculator. Yes, so let's go ahead with the next part. Says state what happens to the value obtained for the concentration of solution Y if not all the water is evaporated in step 7. If all the water has not evaporated in step 7, that shows that the mass obtained here will be greater, right? So if that mass obtained here is greater, then the moles calculated here will also be greater. If the moles calculated here is greater, obviously the concentration of both will be calculated greater, because the numerator will be bigger because of that. So we are going to write the same explanation, that the calculated mass of NaCl, that is sodium chloride, will be higher than actual, so the concentration will also be higher for solution Y. Same applies to solution X also, because if moles of NaCl calculated is higher, then the moles of HCl and sodium carbonate will also be higher, and that's why the concentration calculated will also be higher. So here we ends question 1, and in our next video we'll be solving question 2 of the same paper.